Hey, Jeannie,
Yeah, Brew.
who's our guest on the show today?
Today we have Paul Kirshen. Hi, Paul.
Hi, how are you, Jeannie?
Good to see you. Paul is a professor of climate adaptation at University of Massachusetts, Boston, and research director at the Stone Living Lab. And we're going to hear today about a current Boston report.
Welcome to the show, Paul.
Thanks a lot. It's good to see you again, Bruce, after a long time. So in 2015, we were approached by the city of Boston to develop a summary of the latest science on climate change projections for Boston, for the city of Boston. And we did that, and that was completed around end of the year. And then in 2016, the city used the information in that report, the latest science on climate change, on projections of temperature, civil rights, precipitation, and so on. They used that as input to their vulnerability assessment of the impacts of climate change on Boston. And then about a couple of years after that, we were approached by the city, but also a larger group, to update those projections with the latest climate science. And so we expanded our study area from just the city of Boston to the entire metropolitan area of Boston, the so-called area of the Metropolitan Area Planning Commission. And one of the great things of working in Boston is there's so many great scientists. And so we put together essentially like an IPC caliber team of scientists to help prepare projections of, temperature, civil rights, precipitation, and storms, which could be used by planners and other scientists and citizens in this area to think about how climate change is going to impact them. Now, this report did not translate the impacts into like impacts on transportation or impacts on health. We were really only trying to get the consensus on what are the climate changes, because there's a lot of information out there about what the temperature change might be, what the civil rights is going to be, and we wanted to synthesize all that information and put together the best set of projections, and all of our work had to come from peer-reviewed documents. So, and then also we had a steering committee made up of like people that would be useful, be interested in this information in the region. Then also we had a scientific advisory committee, because this information is really important in dealing with climate change.
That sounds really interesting and important. Were you able to find a fair amount of consensus among the experts and scientists involved in this work?
Yes, we divided into about 5 teams, and every team had about 5 or 6 members on it. And every team was able to review the information and come to a consensus on these are the best projections. These have the most credibility. And I also want to point out that it was a tremendous amount of fun working with these groups of people. I mean, we had great project meetings because the temperature people were very interested in what the precipitation people were finding and what the civil rights people were finding. So we all felt very fortunate we could work on this. And I also want to point out that I was the co-leader. The other co-leader was Ellen Douglas, who used to be at UMass Boston, is now at AECOM. But if you open the report up, you'll see the list of all the other people. We really had the best possible people for every topic. This plot here, which came out in an IPCC type publication, shows various emissions of greenhouse gases in the future. And of course, it's the emissions of greenhouse gases that are causing these climate changes, causing the increase in temperature, changes in precipitation. And so when you develop these projections, you have to think about what's the projection of greenhouse gases going to be in the future. And we have to use scenarios of these projections because we aren't certain for sure what's going to happen. Like, when the Paris Accords came out, we thought there'd be a significant decrease in emissions. But now with Trump elected, who knows? So we need to be able to develop projections of climate change for the various scenarios. And so I'm going to show you temperature changes for a high and low emission scenario of temperature. And, for those that work on adaptation to climate change, like how to adjust to the impacts of climate change, which is really where I do most of my work, we're looking for what we call robust solutions, solutions that will work well no matter what the climate change is. On the left-hand side here, this is for carbon dioxide. These are for other greenhouse gases. This shows like loads, emissions of carbon dioxide. This shows time. So there's 2015 to 2100. And so in this emission scenario, we really get our act together. And starting right now, we have a significant decline. By 2050, we get to net zero emission. We have to actually start taking carbon dioxide out of the atmosphere. This is called RCP 1.9. I won't go into why they're named, but they're named that way. And then at the other extreme, we have RCP 8.5, which is we continue on this rapid increase of emissions. Then we might peak near 2075, and then there might be a slight decrease. And then there are other ranges. Right now, my colleagues in the emission world sort of say we're somewhere on this path here right now, and the target is actually to get to net zero emission by 2050. And I'll get to why that's so important in the next slide. Just remember that 1.9 is net zero emission by roughly 2050. And as you may have heard, the world's best impact scientists have said, look, if we exceed a global increase in temperature of 1.5 degrees Celsius above pre-industrial conditions, roughly 3 degrees Fahrenheit above pre-industrial conditions, if we exceed that, we're going to have major impacts on our ecological, environmental, social, economic systems. And the goal a couple of years ago was, can we keep below 1.5? And this analysis just shows how we're sort of toast right now. This is the low emission. This gets us to net zero emission below around 2050. This, we keep growing over time by 8.5. Under all of these, we hit, this threshold of 1.5 by 2030. So that is really unfortunate.
Or is that 2040, Paul?
Well, so I'm just averaging. Sometime in that time period, we're going to hit. And this is like, right around the corner. We're going to blow through 1.5. And mid-century, they all keep increasing. It's only near the end of the century that we've, 1.9, we've actually decreased below the global threshold of 1.3. But all the other ones, 2.6 has net zero emission around 2070. 8.5, 4.4 degrees, that's about 9 degrees Fahrenheit. So these are extremely dangerous conditions that humanity and ecosystems that support us are going to be facing by the end of the century. So I just want to point this out because it again emphasizes that the most important thing we need to do right now is get to net zero emission. Because if we do, we're going to avoid a lot of these dangerous consequences. But this also shows pretty much no matter what we do, we can't go back to the old climate. The climate of today is not the climate of the future. And so we have to live with a new climate in the future. And so what's going to be some of the characteristics of this new climate? And that's what I'm going to talk about now. So this is a graph which shows, possible change in extreme temperature days in Middlesex County. And this shows, days above 90 degrees Fahrenheit on this axis. This shows years. And this shows, if we have high emission scenario, high emission of greenhouse gases, what the changes are going to be, what the increases are going to be above 2010. And if we have a low emission, what the changes might be. And also notice that the shape of this, like it sort of goes, there isn't much change here, right? No matter what we do, we're sort of locked into this much change. But at the end of the century, what we do now has a big impact. So this just shows like right now, we have about 10 days, well, actually in 2000, we had about 10 days average over 90 degrees Fahrenheit. We're in 2020-ish now, okay? So, we maybe have, 15 or 16 days in a new climate that's greater than 90. And, if you're here in July of this year, you certainly felt that. It was warm. And then, the end of the century, we could have like high emission scenario, 80 days greater than 90 degrees Fahrenheit. That's like almost 3 months. 90 days is 3 months. Every day of the summer is going to be like every day last July, the hottest days in July. And if we get our act together on lower emissions, we may only have 20 days. Okay. It's a lot easier to manage the 20 days than 80 days. For those of us that work in adaptation, we've got to figure out strategies that'll deal with really, extreme future or less extreme future. And that's the challenge of adaptation planning.
When you're thinking about that adaptation, you're thinking about people living in cities and the impacts on human health and what to do about it. And are you thinking also about agriculture and how to adapt? And what are, like, can you kind of list a few of the sectors or ways of categorizing the adaptation thoughts?
Let me back up a little bit. All human and natural systems are sensitive to climate, right? Obviously, a natural system is. But so much of our built environment is sensitive to climate. Like when we design a building, we worry about heating and cooling. We rely upon stream flow for water supply. We rely upon marshes for mitigating coastal flooding. So all of our systems are tied to climate. So the climate is changing, so the performance of all these systems change. So yes, agriculture is going to change because the crops we grow right now in New England don't like really hot weather. Like corn does not like really hot weather. So does that mean a couple of decades we switch to growing millet and the other crops that grow in French West Africa where it's really hot? I don't know. We have to change our crops. They're going to need more water. So we're going to have to use more water. But, water supplies could be limited under climate change. Obviously, people, right? When it gets very hot, we suffer heat stress. Productivity decreases. People can't work outside as long. It impacts recreation. It impacts ecosystems, like water's going to get warmer, like streams and rivers. A warmer body of water holds less dissolved oxygen. And like we like oxygen, so do fish. So DO is going to go down. Also, ocean fish are like, they migrate according to temperature. And it's like cod likes cold water. We've already seen decreases in cod south of the Cape Cod because it's gotten really warm there. And lobster is like disappearing, south of the Cape. So all these, but fish can move, right? But something like a tree, it's tough for a tree to move. So we could see a lot of trees just dying because of the extreme heat. And then I just want to point this out also. One of the biggest themes is, besides the uncertainty, is the social justice aspect of climate change. So this just shows a heat map of Metro Boston in 2020. And the lighter areas are where it's hot. This shows a map of Metro Boston, and the various colors show areas where there's environmental justice communities. And the color refers to the kind of EJ community it is. But you see almost a one-to-one correspondence between where there's extreme heat and where there's EJ populations. And so, what this means is, the EJ populations generally have this is true throughout the world. The world's poorest have the smallest carbon footprint, but they're going to suffer the most. And they have the least resources, what we call adaptive capacity, to deal with it. So there's a huge social justice dimension of all the work on climate change. So just keep that in mind. So anyway, back to the impacts. So what's going to happen to storms? So, coastal Massachusetts, we have extratropical cyclones. These are like winter storms, nor'easters. So we get these in the winter. And then we have tropical cyclones, so-called hurricanes. Then we get convective storms, which are thunderstorms. So, this is really tricky science. And there's a lot of uncertainty. So in parentheses is how certain we are about a change. So, like, for example, our nor'easters, right? There's going to be an increase in precipitation in our winter storms, but less if it's going to be snow. That's going to be warmer. And then hurricanes, right? So we know there's going to be an increase in intensity. And that's in the news all the time because all the waters in the Atlantic Ocean are so much warmer now. So they fuel the hurricanes. And warm water holds more rainfall. So more rainfall. So these are what's going to happen to our storms. And then this is a very busy graph, and I'm sorry for it, but this shows changes in our precipitation. And, globally, annual rainfall has increased, but the distribution has not been the same throughout the world. So in the mid-latitudes, like New England, our annual rainfall has increased. But around the equator, the annual rainfall in many cases has decreased, which is really unfortunate because around the equator, there are a lot of countries who depend upon rain-fed agriculture, and they're generally poor. So it's another example of the social injustice aspect of climate change. So anyway, this essentially says that our annual precipitation is going to increase in Boston, but might decrease in the summer and fall seasonally, but increase in the winter and spring. And again, this is unfortunate because summer is our warmest temperature. And so what it means is our stream flows are low in the summer anyway, but they could be lower than now because less rainfall, and it's going to be warmer. So there could be less flow, warmer, so that'll mean less dissolved oxygen for fish, for example, and more stresses. And then another change, right? So when we design infrastructure, like a storm drainage system, we design for a so-called extreme event. We don't design for average rainfall. We design for extremes. And one of those extreme conditions is a 10-year design storm. So this is the amount of rain that falls in a 24-hour period that occurs once in the average every 10 years. It really means like every year, there's a chance of 10% that amount of rainfall will be equal or exceeded. Okay, so typically we used to design our urban drainage networks for this. And so let's just look at Boston, what's going to happen. So Boston is sort of this greenish color. This is the low emissions, right? Sort of right here, okay, the green dash line. The green solid line is high emission change. Right now, it's about 4.5 inches. In the 1970s, this value was around 4 inches. Now it's about 4.5. So under the high emission scenario, it could be like 6 inches by end of the century, or it could be, 5.5 inches. But the point is, it's bigger than it is now. So it means like all of our urban drainage systems have been designed for this much rainfall, but they're all out of date now because it's going to increase in the future. So if you're in an area that has like street flooding now and you get a major storm, it's only going to get worse in the future. Oh yeah, and this just shows, this is Boston. All these little circles represent a point where a catch basin overflows because of rainfall. And so you see it in large parts of the city. And so obviously when the rainfall increases, these catch basins are going to overflow more, and there'll be more catch basins overflowing. And what happens when these things overflow? Where's the water go? So some of it goes into people's basements. Some people have apartments in basements. It floods into streets. It can impede the response of emergency vehicles. It can result in standing water, which is unhealthy because mosquitoes can breed there. The extra runoff can go into the rivers. Urban runoff is not clean because there's a lot of guck on streets. So it can decrease water quality and so on. So street flooding is a multidimensional problem. Okay, another one is river floods. Okay, so it's a small flood. These occur like once every 2 years. 100-year flood occurs once in the average every 100 years. So like a major reservoir is designed for a 100-year flood. A little tiny reservoir, if it floods a lot, it's okay. But the discharge volumes in these are going to increase significantly in the future. So if you have a reservoir designed for this now, the flow is going to increase maybe 15 to 70% by the end of the century. So that reservoir will be non-functional, will not be able to function as a flood control reservoir. Okay, groundwater. So much of Massachusetts, particularly that outside of Route 95, depend upon groundwater for local supply. Plus, groundwater is really important because it supplies inland marshes with water. So this just shows the amount of water that goes into the ground right now over a month of the year as is measured at Pepperell, Mass., which is a town about 40 miles west of Boston. So essentially, in the winter, there's a lot of snow on the ground. In the March, it starts to melt. A lot of that water goes into the ground. And then over the spring, it decreases. in the summer with a lot of evaporation, even though there's rainfall, there's like no recharge. Then it goes up again in the fall with the decrease in evaporation because of decrease in temperature. Anyway, what this says is that groundwater recharge is going to decrease in the spring, and it's going to increase a little bit in the fall, but the increase is not going to offset the decrease. And so our groundwater levels are going to be dropping in eastern Massachusetts. And then sea level rise. So in Boston, we've had about a foot of sea level rise in the last century. And 6 inches is because of, global climate change, melting of ice on land, like the Greenland ice sheets, ice in the Arctic, and also thermal expansion. What's going to happen in the future? Again, this is a range, right? So this is the increase since 2000, right? So we've already had a foot. So, end of the century, it could be as much as 2 to 5 feet. This is like a likely range, okay? There's a high probability it's going to be within this range. But there's also a 1 in 1,000 chance it could be 15.6 feet by end of the century. And that's because up until around now, most of the sea level rise has been because of the thermal expansion of the ocean. And that's easy to model because we know how water responds to heat. Most of the change going forward, there's still going to be thermal expansion. The big uncertainty is what's going to happen to these ice sheets. It's only in the last decade or so we've really begun to understand the dynamics of ice melting on land. I mean, it's a really, really complex field. And so there's a lot of uncertainty. That's why it could be almost 16 feet by end of the century. 1 in 1,000 chance, but it could happen.
So these are not storm surges or any particular weather day. This is an actual high tide on a given day.
Average.
Yeah. And we already have areas of like Boston that flooded high tide, like down near the aquarium, Morrissey Boulevard, all over the place. And so just think about any beach you might like, whether you go there in the winter or summer, add 5 feet to that high tide level.
It's gone.
Right. And of course, with the higher seas, storms come in higher. And our hurricanes may actually be more intense. And so the Cape, south of the Cape is vulnerable to hurricanes. And so places like Nantucket, the Vineyard, all the Cape is really facing a huge amount of problems. Plus, it's not just, flooding. It's also, higher sea levels cause more erosion of our beaches and marshes and things like that. And it also interferes with all our street drainage, because a lot of our drainage goes into the ocean, right? In Boston, if the ocean's higher, water seeks its own level. That water in the ocean could come up and block drainage pipes. And so the water has no place to go. So this is going to, make street flooding worse. So a lot of negative impacts of climate change on Massachusetts.
This is a lot of bad news.
Yeah. I thought this show was supposed to be fun and lighthearted.
What are we going to do about this? Do you have any solutions?
Yeah. Actually, one thing we're going to do is write more reports. So this report was on, sort of changes on the land, precipitation, temperature, sea level rise, and those are the major factors. We also did a special report on groundwater. And then we just released a special report on the marine environment. What's going to happen offshore. And again, there's no good news about what's going to happen in these places. But getting back to what we do about it, so obviously, as I said earlier, the most important thing is decrease our emissions, right? And then actually start figuring out a responsible way to take carbon and other greenhouse gases out of the atmosphere, okay? I think we know how to get to net zero. Your energy friends, we know how to do that. We know how to switch to renewables. It's not happening. Market forces right now are driving the transition, and some government investments. But we have to do everything we can to get to net zero. Okay, and the whole world has to do this, right? It just can't be the U.S. or Boston or Massachusetts. We all got to do this. So, and the big emitters, U.S., Europeans, China, India, Brazil, we all got to get down there. But also we got to figure out how can we let developing or less industrialized countries, how are they going to get their energy? How are they going to leapfrog over the old ugly fossil fueled energy systems? As I said earlier, we are going to have to adjust to the changes because we really can't go back to the old climate. And that's the field of adaptation. And that's what I spend most of my time thinking about. And the challenge of adaptation is we really don't know what we're planning for. If we knew what we were planning for, if we could even assign probabilities to the future, there are well-known, operations research, symptom analysis techniques we could use to address these problems. But we don't have that luxury of certainty or even probabilities. So the field is called playing under deep uncertainty, decision-making under deep uncertainty. And the way to think about it is, think about coastal flooding. We could say, okay, Boston could flood by 5 feet by end of the century. That's a reasonable worst case. So let's surround the city with 5 feet of a seawall. But say we only had 2 feet, we would have overinvested. So let's just build a seawall right now that's like 2 feet, but let's design it so we can add on to it over time as the climate changes. It's adaptive management. You want to adjust as the uncertain climate unfolds. And you want to preserve your options for the future. So we want to think about, again, adaptive management, incremental planning, robust decisions that work well no matter what the future is. And this kind of thinking can apply to any kind of infrastructure system. We know how to do this, okay? This kind of planning. And it requires, more traditional analysis than saying, okay, the rainfall is this, let's design for this. It's fairly sophisticated. It's a little more expensive, but, we're talking like for the city of Boston, just on sea level rise alone, spending $5-10 billion over the next 20, 30 years. So we should be investing in the best planning methodologies. And now one challenge is protecting ecosystems, and they are really important to us. And for a whole bunch of reasons. You just look at the field of ecosystem services. And that's a little trickier because ecosystems are less manageable by humans. So, and there's a lot of them. And so what can we do? Well, we can make sure ecosystems are healthy, right? If they're healthy, they might be able to adjust. We can help them adjust. So if you have a coastal marsh, because of sea level rise, may eventually just turn to open water, unless it can naturally migrate upland onto a beach, go further inland. So what we can do, we can make sure there's less development blocking that marsh so we can naturally move inland. And the other thing we can do is try to protect it. So all of a sudden, this is another crazy thing. We have all these forest fires in eastern Massachusetts. We never had these growing up. And now they're part of our landscape. You look at some of the early reports on climate change, we knew they were coming. Say we have a really important ecosystem, some kind of trees, we can put a real good fire break around that and try to protect that ecosystem. But the natural environment is so large, it's difficult to protect, particularly, like I mentioned, we just did this report on impacts of climate change offshore. We're changing the Gulf Stream, okay? The Gulf Stream brings up warm water from the south. And with the changes in temperature, we're slowing down the Gulf Stream. Huge implications. We can't re-engineer the Gulf Stream. We can, re-engineer our coastline, okay, to sort of deal with coastal flooding to the end of the century. We can't re-engineer the Gulf Stream. We can't change the mix of nutrients on Georgia's bank, which is so important for the fisheries. We can't do that. The only way we can control those systems is cut down greenhouse gas emissions. We can build, flood walls. We can build parks, nature-based solutions along our coastline. We can't re-engineer a lot of this stuff that's really important for us. And so I don't know what the answer for that is. We're going to have to just adjust to less fish, less nutrients, warmer coastal waters. a slower Gulf Stream, and it stinks. And the killer is, as you know, this is all unnecessary. Like we've known about serious consequences of climate change since the 1980s or so, or certainly the 1990s. And we just, for all sorts of terrible reasons, it's been ignored. And now we're going to pay a tremendous price. It's going to be really expensive. We're like this $5 billion we're going to spend in Boston for coastal flood protection. We're going to spend it over time. It's going to make the coast more attractive because we're going to use nature-based approaches. It's going to be greener, okay? And so it has good social benefits, good environmental benefits. But that $5 billion could have gone into education, healthcare, better mass transit. It would have had a huge impact on the quality of life. We didn't have to spend this damn money. Plus, the other thing is the whole world is going through climate change at the same time. So we have a little bit of a problem now with migration from the global south to the north. That's all going to get amped up and amplified because of climate change. And we can't even handle it now. What's going to be like when it's worse than now? And also it's going to be, a lot of the world's going to be unstable, politically unstable because there'll be a lot of unrest.
It's pretty scary, but I don't want to miss the chance for our viewers to hear as kind of a final word about the good work you're doing at Stone Living Lab. I mean, I imagine it's related to the nature-based solutions you're mentioning, but we just have a minute left.
So based upon a report that UMass Boston wrote and that I led, the city committed to using nature-based approaches to deal with coastal flooding. And a nature-based approach is some system that's engineered, but it mimics nature. And so the idea being, like for Boston, instead of building a concrete seawall along the coast, let's build parks. And the elevation will protect against the flooding. And we can add on to the park over time as the sea level goes up and flooding goes up. On the coastal side, we can create an ecosystem, so we improve habitat. And then the top of this park, we have, parks. So we have, playing fields, trees, and that has provides amenity to a community, particularly a community like East Boston, which does not have a lot of trees, does not have a lot of open space. So great, city commits to nature-based approaches along the coast. The problem is there's a lot of gaps in our understanding of the biophysical and social economic aspects of nature-based approaches. And so, for example, we don't know the lifetime of a nature-based system up here. We have a very strong seasonal climate up here. What's going to happen in the winter if we have all these plants? Social economically, if it makes an area greener, are we going to speed up gentrification? How do we make sure the benefits actually accrue to the population we want it to go to? So the lab was founded, generously funded by the Stone Foundation, to carry out research on the biophysical and social economic aspects of nature-based approaches. So if you go to our website, stonelivinglab.org, it's got a lot of material on it. And it's only getting better. We're doing really exciting work. It's a great partnership of the UMass Boston, Boston Harbor Now, the Commonwealth of Massachusetts, the City of Boston. And we also work in consultation with the Massachusetts Tribe and also work with the National Park Service. So it's all hands on deck.
That's great. And that's exactly what we need. And it's a message of hope that keeps our eyes open and our feet kind of running toward the goal, because we got to be all in on this. I totally agree.
Yeah, exactly right. And again, it's unfortunate, but we have to be all in. It's all hands on deck. And, it's going to create zillions of jobs, And
it's really beautiful, inspirational stuff that you guys are doing. And I think that's the one thing that gives me hope is there are so many great minds working on so many different workable solutions, and we're just got to keep on doing it. So It's been great hearing from you.
Thanks for being on the show, Paul.
I appreciate the opportunity, and it's unfortunate we're going to talk about this stuff, but I'm glad we are. Thank you very much.